Pytorch to make a large language model. So before I get into the actual code, I just want to mention that this is all on GitHub, and there's some setup instructions on specifically downloading CUDA and a few other things to make this actually run on your graphics card. I'd recommend using something like a 3070 or around that kind of tier graphics card, because this kind of stuff does take a while. And I ran this for about 3 or 4 days until it started making actual readable sentences with like proper grammar periods at the end. So this actually works, and if you run it on your graphics card for a few days, it'll give some decent results. But if you actually wanted to give some more useful responses, you'll probably need to run it on your GPU for like 3-4 weeks. Maybe even 2 months if you really wanted to. Basically, overall, the way this works is we use a Hugging Face sample, 10 billion token one specifically, and we save this on a bunch of batches, and then we train a large language model. It's basically similar to GPT-2, and it actually uses the GPT-2 tokenizer as well to train on it, update the weights and biases, and get some good outputs. So make sure you have CUDA and all that kind of stuff installed. If you run into issues, I know it's really finicky. It took me a while to get this to all work. I would recommend starting on Google Colab. It's just super simple to get it running on Google Colab, because you don't need to mess with all of this stuff. But if you do want to run it on your computer on VS Code, something like this, then just use ChatGPT or the internet to help you with all the dependencies and random stuff you need to download, because it does take a lot of effort. So what I've created here is I have a data.py, which you should run first, and then a main.py, or run the model.py to initialize the model, and then run the main.py. But I've put it all into this mini GPT Jupyter notebook to make it simple for you to use. So up here we're going to pip install Torch TQDM. This is just for progress bars. Transformers and datasets is for the tokenizer, and also for the actual Hugging Face dataset. First we import all of these, not much to discuss there. Before we get into this, I just want to say I'd recommend cloning this onto your own computer and trying to get it working, because that's one of the best ways to learn how this stuff works. And just messing with different values, making the model larger or smaller, and just that's a great way to learn how these things work, and just reading the code and trying to adjust it yourself. So yeah, let's continue. So we have this output directory called token batches. That's what you see here. This is currently running on my computer, and right now we're at token batch 22. I'll talk more about that in a sec. And then here we make this directory if it doesn't exist yet, so we're running this. Then we want to load the dataset from Hugging Face. So I just have this print message to print that we've gone to this point. The dataset we're going to load is the Hugging Face FindWeb 10 billion token sample, and we're going to have a training split. Okay, so we're going to initialize the GPT-2 tokenizer. I just have another print message here to make that clear, so that when it's running down here, you can see loading the dataset, initializing tokenizer, starting tokenization, and then you can see all of these. Yeah, this just uses the pre-trained GPT-2 tokenizer. In this video, we're not really going to go in deep into tokenizers. There's some good videos by Andrei Karpathy. If you're interested in tokenization, definitely watch this video.
Hi everyone.
It's really good. He goes into depth about all of the specifics of that. But here we're just going to use the pre-trained GPT-2 tokenizer. So here we're going to tokenize the data set. So we're going to have 10 million tokens per file. So as you can see, each of these files has 10 million tokens. And a token is kind of like a sub-word section. Like, you can kind of think of it as like syllables or like little pieces of words that are a few characters but not fully words all the time. This all tokens will hold the tokens that we currently have, and here we're going to count the tokens and count the files. This is just going to help so that when we hit the 10 million count, we save it to a file and name the file with the number. And we're just going to use the start time because we also want to print how long each one takes. Okay, so here we're going to go through all the text in the data set, and basically what this code does is it takes the text, it tokenizes it, adds it to the all tokens, and then here if the token count is above tokens per file, which we've set to 10 million, it'll here it makes a new file, with the file count name, the number, and saves all as a torch.tensor all of the tokens. So this is really efficient for training because everything's already tokenized. When we're training, it can quickly just read all of this, and it just goes much quicker once it's saved like this as a tensor file. And here it just prints saved file path with this many tokens. It increments file count. All tokens is reset to clear the memory, and then token count is 0. The other reason we limit it to 10 million is because if this is constantly, like, if it makes a giant file, you could run out of memory and it could cause other problems. This just makes it a lot easier. And as you've probably noticed, since we're doing the 10 billion token sample and each file has 10 million tokens, it means we're going to reach 1,000 token batch files. From my experience, I ran this a few weeks ago. It took a few hours at least, like maybe 5 to 12 hours depending on your computer. So yeah, it does take quite a few hours to run this. So now I'll get into this bottom remaining section of the code. So after it's done going through the loop, it'll save any remaining tokens because we might not round it perfectly, because you can see here sometimes it saves a bit over 1 million tokens. I'm not completely sure why this happens, because we are just reading until it gets to 10 million, but it is what it is, so we save the rest of the tokens. If this doesn't work and we can't read from the tokens, it'll give an error. And then here it gives the elapsed time, and it'll print that everything's finished within this much time. So here you can see. Okay, so now I'll continue with the rest of the code. So this is the actual model code. So first we have to pip install torch and data classes, and here we import these. So this is just the GPT config, which we'll look at a bit later, but this is when we configure the block size, vocab size, number of layers, number of heads, and the dimension of the embedding space. Okay, so here, this is the tokenized data set. So this basically allows the model to read the batches that we've tokenized. So we initialize it here. Okay, and then to read the tokens here, we get the tokens, we load it from the file path, which will be in the folder here. And then for each in the range 0 to length of tokens, yield the tokens. So, and now for each file in this iterates basically through each of the files. So it goes through each of the files and it'll print the file path, total tokens in file, and then total batches in file. So this total batches in file is basically calculated through total tokens divided by the block size plus 1 divided by the batch size. So this is like basically a 2D tensor, you can think of it, and so you can divide the total tokens by this and it'll give you the total batches. And here it loops through each of the tokens, and it's got the input IDs and the labels, and so it'll yield these. So this is the input into the neural network, and then these are the labels where it'll change the weights and biases to try to match these as the outputs. Okay, going into the transformer blocks, so here it initializes it. It's got a sequential layer with a linear layer, a GELU, and a linear layer. You can mess around with this as well, change it to ReLU or change it to sigmoid function or something else. This seems to be the most efficient and work the best with this. It's got layer normalization, and it's got the multi-headed attention block here as well before that. So these are all important steps. I recommend reading the documentation. I personally fully don't understand how all of these work, but I am working on reading the documentation and trying to understand as much as I can myself, because like originally people would have to write each of these blocks themselves, and it was a much more complicated process, and you couldn't just write lost dot backwards and it would figure it all out for you. So I think it's important for people to actually understand how these things work. I will admit I don't fully understand how they work, but just reading the documentation helps. So that's one thing I would recommend. And this is the forward function. So it basically goes through the self-attention. And then this is a multi-layer perceptron, and then it will return X. Okay, and so then here at the bottom of the file, the GPT class. it initializes it. So the token embedding, the position embedding is just full of torch.zeros to initialize it, and then the blocks, it initializes it as a sequential layer as we saw up here. Now I'll just move on to the forward pass. It just goes through each of the layers. So, and one key thing here is it puts it on the right device. So if you have a GPU available, it will put it on the GPU and use that. Otherwise, it'll use the CPU. And there's also this unsqueeze. I don't completely remember why this is important, but it will not work without it. And then yeah, this is the token embeddings plus the position embeddings, and then it goes through the blocks, which is just the sequential layer, and then the layer normalization. And then it will return the logits, which is basically like the unprocessed output, like the prediction of which token will come next. Okay, so now we're down to the final actual training loop and this kind of important stuff. So we're gonna pip install this stuff, TQDM for, as I said earlier, for the progress bars, and then import all of this. You can also change it to 16, but I found that 32 works well with the amount of RAM on my computer. I have 32 gigs of RAM. I guess just adjust this so that you can get a high value, because it'll make training faster. But don't overdo it, because then it'll start to slow down because it can't all fit on memory. The accumulation steps is, it does 4 steps, and then it'll adjust the gradient. So this is basically the same as having a batch size of 128 if you had more memory. So this simulates if you have more memory. It's not extremely useful, but I included this just because a lot of neural networks have this. And if you want to get close to the exact way that they train GPT-2 and stuff, then this will be important, because you probably don't have like tons of RAM on your computer. And this will just print every 200 batches. This line just sets the number of workers to os.cpu count, so this will set it to 8 on my system because I have 8 CPU counts. I believe it's 8. And so this just means it'll load it quicker because it's using more CPU cores. This just saves the model and optimizer. So the reason it also saves the optimizer is so you can continue training. So it takes in the model optimizer, the epoch number, and the file ID, the file index, and it makes this directory called checkpoints if it doesn't exist. Checkpoint path is it goes into checkpoints and then names it GPT-2 epoch, and then the epoch number and the file index. So this is nice because if you run it for like weeks at a time, if you're on vacation or something, it will each batch, we'll see later on, it saves the model, and then each epoch it creates a new file. So this means you don't run out of system memory, or like storage I mean, on your hard drive, because each save is quite a lot. We'll see later how much it actually is, but it also saves multiple files in case one of them doesn't work for some reason or something goes wrong. This is the checkpoint, saves the model state dict, the optimizer, the epoch, and the file index, and here we use torch.save, and then we print that out. Now here, to load the model and optimizer, we, to sum it up, basically load the most recent checkpoint that we've saved. Won't really go into depth on this because it's not super interesting, but basically it loads the most recent checkpoint that we saved. This function generates text, so sets it to eval mode so that we're not doing dropout or anything like that, although I'm not sure if this, I don't believe this model does have dropout, but it's important to set your model to eval mode, just good practice. And then this is the input tokens basically, and it encodes them because we input it as text, as normal text. It encodes them and puts it onto the right device, so the GPU or CPU. And now it goes through 40 tokens and basically predicts the next token over and over again 40 times. This is a long line which just does a forward pass. No, this doesn't. This does the forward pass, but this actually goes through the softmax, and then will actually give us the output, the next token. So then we have the generated text, which it decodes it back to normal text and then prints this. So it'll print your generated text after that. Basically this, yeah, I'll talk about this more later. But then we have the train. So this is the actual training loop. So here we have the start epoch is, we get it from the loaded model optimizer. So this is, like for example, if you're on epoch 3, and you turn this on because you want to do some training on your model on your computer because you'll be gone for a few days, then it'll just load the most recent one and set the start epoch to whatever it's on. We have a print statement here that just says starts training, and then these are just to get it to start training. So we set the scaler to grad scaler. We do model.train. Start time is equal to the current time, and also the last print time is equal to this current time. We opened the loss.txt, so this is just, you can see here I trained this for a few days and got the loss down to 5.8. Once it gets down to like 5 point something, you start getting decent, decent sentences that actually kind of make sense. And that was on epoch 3, but I started at epoch 2, so basically like one full epoch. And now it goes through, it just says 5 epochs. You can change this 5 to whatever you want. It's probably not good practice for me to hard code this in, but it does 5 epochs more. And it goes through each of the batch indexes. And then sets the input IDs and labels to input IDs, sets them to the device. It moves them to the right device. That's what this line does. Set the optimizer to optimizer.zeroGrad, and then with autocast, logits is equal to model input IDs, and the loss is equal to neural network cross entropy loss. I recommend you read about this on the documentation. Yeah, this just says the cross entropy loss to calculate the loss. Then we do the dot backwards. And then here we look at the accumulation steps. So if it's set to 4, that means every 4 steps it will do these. It will step the optimizer, which means it will basically calculate the weights and biases the way they need to be changed. It will update the scaler, which actually updates them, and then it will optimizer.zeroGrad again to continue training. Now down here, tokens per batch is the number of tokens in the batch. So it's like 10 million-ish most of the time. It sets the current time, sets the elapsed time, and then tokens per second is calculated by this formula. It's basically just how much time since the last print, how many tokens per batch, and then that's divided by elapsed time if elapsed time is above 0, because we don't want to get a divided by 0 error. And then here we'll just print a bunch of useful information. The thing you want to optimize here is keeping everything the same, but just using getting a higher tokens per second. That's the main important statistic that you want to look at here once you're actually training. And yeah, so then it will save the loss to the file I just showed earlier. That's kind of useful if you just want to make a graph in like a spreadsheet or something of the loss going down. Okay, and then here, if the batch index is every 1,000 batches, basically, we'll save the model in optimizer and generate text for I am and it will continue this. So this is important to just check how it's working over time. It's nice to see in the terminal while you're running it. It slowly improves. It's actually quite interesting to watch. And once it's done training, it'll just print this. So in the main method here, we initialization and data loading. So this gets token files. This configures our GPT. So this uses similar values to GPT-2, the smallest model. This specific model is around 160 million parameters. So block size 128, vocab size 50,000 to 157. This is actually because there is they trained it for 50,000 tokens, and then there's 256 for all the different characters, and then there's one more for the, I believe it's the end token. 12 layers, 12 heads, and the embedding space is 768. The data set is tokenized data set, it just loads it from above. And the loader is the data loader that we define above. We set the device to CUDA if it's available, otherwise CPU. This is important because if you keep seeing CPU, that means you haven't properly installed CUDA. If you have a graphics card like a 3070 or something like that, it'll actually print what device you're using, so make sure it's GPU, or CUDA, it should say. The model is the GPT config that we have here, and it puts it onto the right device, onto the GPU. The optimizer is the Atom W optimizer. This is widely used. You can read about it, and the learning rate is 3 E negative 4. That's what I found to work pretty well. Tokenizer is just the GPT-2 tokenizer fast. This is basically the same as the normal GPT-2 tokenizer, but it's just a bit quicker without any downsides basically, so just use this. And here we just call train. So this all trains a model similar to GPT-2. The reason you're not going to get something like GPT-3 just by training this on your computer is because GPT-3 has many more parameters. First of all, it has around 7 billion parameters, whereas this has 160 million, so it can just store a lot more data, a lot more information from the web. And the second thing is that there's a post-training stage where they kind of like fine-tune it and get it to answer queries properly, because this is basically just a token prediction machine. You can type up something and then it'll just continue typing it as if it could be a random article from the internet that it just continues based off of, or something else. So you're not going to get something like GPT-3 with this, but it's great for learning, great if you want to actually understand how these things work, and I'd recommend just going to the Pytorch documentation and just reading through this. I go through this every once in a while just because, yeah, they've got a lot of like functions that people constantly use, and definitely good to know how these things work. So yeah, that's basically it. If you have any questions or you need any help, leave a comment below. I'll definitely read all of them. You can also use the internet to help yourself out, like Reddit or other sources. So yeah, that's basically it. Leave a comment down below telling me some feedback on this video, and I'll see you next time.